everybody, and welcome back to Math 105 for the final week of the semester. So, just to give you a bit of a heads up, I know I mentioned this in my email, but Monday and Wednesday this week we're going to be covering Standard 20. Friday, I'm not going to post videos / have an official class because Thursday and Friday you're going to have one last midterm to complete, exam number 4, and then finally, we'll have another exam similar to exam 4, slightly different rule set, that'll be the final exam. And exam 4 and your final exam will be kind of your last chance to get masteries in any standards that you're still missing out on. So as far as the agenda for today goes, we're going to be doing the first half of Standard 20, talking about quadrilaterals. I've got office hours, my usual office hours, today and Wednesday. 10 to 10:50, 2 to 2:50. Tuesday, my morning office hours I have to cut a little bit short because I have to be on call to interview someone for a position here. So Tuesday morning it'll just be from 10 to 10:50, and Tuesday afternoon from 2 to 3. And as far as homework for now goes, standard. Don't forget, if you haven't done the Standard 19 quiz yet on hyperbolic geometry, that's due tonight, Monday night. And keep in mind, exam 4, the fourth and final midterm, is going to be at the end of this week, which you're going to have Thursday and Friday to complete. Okay, what insect is best at math? The insect that is best at math is the acactant. Okay, so probably been a while since you've kind of been watching these videos. So I thought we'd start with a little bit of a brief review of the last two standards. Remember, standards 18 and 19, we're looking at models of non-Euclidean geometry. In other words, models of geometry where the Euclidean parallel postulate, Euclid's postulate number 5, was replaced with one of two different versions. In Euclid's version of the parallel postulate, this is the modern version that's logically equivalent to what Euclid wrote, it says that given any line L and any point P, there exists a unique line M through P that is parallel to L. In other words, there's only one line that is both parallel to L and passes through the point P, and that would look something like that. And Euclidean geometry is where this Euclidean parallel postulate holds true. In hyperbolic geometry, we have a different version of the parallel postulate that holds true. In hyperbolic geometry, we said that given any line L and any point P not on L, there have to be multiple lines, at least two, that pass through the point P and are also parallel to L. So let's say this is one of them, a line M, and maybe this is another one, line N. And any model of geometry where this hyperbolic parallel postulate is true is called a model of hyperbolic geometry. And we saw one of these types of models back in Standard 19 when we were looking at the Poincare disk model. And finally, the last model of hyperbolic geometry we looked at was elliptic geometry, or the elliptic parallel postulate, where in the elliptic parallel postulate, no two lines can be parallel. Every pair of lines must intersect each other at least one point. So in this case, you have lines L and M. They may start looking like they're going to be parallel, but eventually they will have to intersect if the elliptic parallel postulate is true. And the model of elliptic geometry we've seen, where this postulate holds true, is spherical geometry, where our lines were great circles on the surface of a sphere. So what I want to do, so in the last two standards, standards 18 and 19, we talked about several different ways in which lines and triangles can behave in elliptic versus hyperbolic versus Euclidean geometry. And so in this final standard, I thought it would be interesting to kind of look at quadrilaterals. In other words, shapes made up of that are kind of surrounded by 4 lines instead of 3, like a triangle, and how do quadrilaterals behave differently across these 3 different systems of geometry. And in today's class, I want to talk about Sarcari Quadrilaterals, named after an Italian mathematician, Sarcari, who lived 100-ish years ago and change. So a Sarcari Quadrilateral is going to be a quadrilateral, ABCD. This symbol right here, looks like a square, is just a generic symbol to refer to a quadrilateral, sort of like how we would use something like this to refer to an arbitrary triangle, ABC. Here, this notation is used for a quadrilateral. A Sarcari quadrilateral is one ABCD in which two things have to happen. Here's going to be our example. The first thing we need is that the base angles A and B are right angles. So we have to have this holding true in our Sarcari quadrilateral. And the second thing that has to happen is the two sides of this quadrilateral that are vertical, meaning AC and BD, have to be congruent to each other. In other words, sides AC and BD we're going to assume are equal. And any quadrilateral, whether it's in a model of Euclidean, elliptic, or hyperbolic geometry, that satisfies these two properties, that AB, the two angles at the base of the quadrilateral, by base I just mean kind of the ones at the bottom here. If these are right angles, and if AC and BD are equal in length, then we say this is a Sarcari quadrilateral. So let's take a look at this. Let's take a look at this shape. What do you notice about it? Well, A and B are right angles. It certainly looks like C and D are right angles as well in the picture that I drew. And it certainly also looks like that AB and CD have the same length as each other. So we might want to consider that question. Do we know if we have the base angles A and B equal, and if the sides AC and BD are equal in length, do we also have to know that the other two sides are equal, the top and bottom, the base of the quadrilateral and the summit of the quadrilateral? Base and summit are just kind of fancy ways of saying the bottom of it and the top of it. Do we know in a Sarcari quadrilateral that if the two sides have the same length, and if these are right angles, do C and D also have to have right angles? And does the length of the base from A to B have to be equal to the length of the summit from C to D? And that's going to be an interesting question. It's going to turn out to be the case that in Euclidean geometry, those all will have to hold true. But in hyperbolic or elliptic geometry, we might be able to construct Sarcari quadrilaterals like this, where the summit and base have different lengths, or where C and D maybe do not have to be right angles. So let's take a look and see if we can kind of prove, / look at some examples of some of what I'm talking about. So before I look at the non-Euclidean versions of these Sarcari quadrilaterals, I think it would be good to look at a proof that has to hold true in all three versions. And this is going to be a proposition. And get rid of this too. And in this proposition, we are going to prove that the summit angles of any Sarcari quadrilateral must be congruent. Or must be equal, let's say. I.e., it has to be the case that angle C and angle D are going to have to be equal to each other, assuming we're working in a Sarcari quadrilateral where A and B are have right angles, and AC and BD are equal. We can prove as a proposition that if we have a quadrilateral like this, the angle at C and the angle at D are going to have to be equal to each other. So let's see if we can prove that. So, Dr. Gerstle, you didn't give us a proposition number. So this is not a proposition that was in Euclid's Elements. Euclid didn't have any notion of this idea of Sarcari Quadrilateral. This idea was kind of came up with by a mathematician, Sarcari, who lived in like the 1900s, way long after the age of Euclid. So this is not one of the propositions in Euclid's Elements. This is something that Sarcari himself proved thousands of years later. So the proof might read a little bit differently than the ones from the Elements that we've been looking at. So let's see if we can prove this. I'm going to draw a little picture down here so I can refer back to it without having to go to the other goal. So we're going to assume that we have a Sarcari quadrilateral, meaning we have right angles at A and B, and that AC and BD are equal to each other. Well, since we know that AC is equal to BD, we know that because we're assuming we're working over a Sarcari quadrilateral. We also know that AB is equal to itself in length. And finally, we also know that the angle CAB is equal to the angle DBA. Why do we know that? Well, that's just the same as saying this angle down here at A is equal to this angle down here at B, which we know they're equal because they're both right angles, and all right angles are equal to each other. So we know AC is equal to BD. AB is, well, it's equal to itself. Let's put a single triple hash mark down here to say this side's equal to itself. And the angle between AC and AB is equal to the angle between BD and BA. We know two sides are equal and the angle between them is equal. That's right. We're going to use side angle side to say, if we make diagonals down the center of this quadrilateral, we're going to use side angle side to say that the triangle ABC has to be equal to the triangle BAD. Because we know that the two sides on the side are equal in length. The bottom side is equal to the bottom side in length. And the angle between the side and the bottom of each of the triangles are the same. Side angle side will then tell us these two triangles, ABC and BAD, are going to have to be equal to each other. So then we can say that by side angle side, proposition 4 in Euclid's Elements, we know that the triangle DBA is equal to the triangle CAB. DBA equal to CAB, which in turn, what we want to get out of this is that BC and AD are equal to each other in length. So the reason why we want these two triangles to have to be equal to each other, this one and this one, is because we're going to use side angle side to tell us these two sides, the hypotenuses of these right triangles, are going to have to be equal in length, which I'm going to denote with these double hash marks. So AD has the same length as BC. And that's going to be important, that AD and BC are equal in length. So now, we're going to do something else. We're going to show that not only are the bottom left triangle, is the bottom left triangle equal to the bottom right triangle, we're now going to prove the top left triangle, ACD, is equal in length, or is equal, not equal in length, is just equal to the top right triangle, BCD. And we're going to use another one of our favorite triangle congruence propositions, side, 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 in order to do it. Because one thing we know is that CD has to be equal in length to itself. The hypotenuse of this top left triangle and this top right triangle are equal in length. That's what we just proved up here. And finally, we're going to use that AC and BD, the sides of the top left and the top right triangle, are still equal to each other. Side, side, side is then going to tell us ACD and BCD have to be the exact same triangle, which will then tell us that this angle here in the middle will have to be equal as well. And that'll end our proof. So let's write that down. And then since CD is equal to itself, BC is equal to AD. That's what we just proved in the previous section using side angle side. And since AC is equal to BD in length, that's just the two sides being equal, part of this being a Sarcari Quadrilateral. Since we know all of these are equal, by side, 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 we know that triangle DCB has to be equal to triangle CDA. So in other words, this triangle in the upper right of the quadrilateral has to be equal to this triangle CDA in the top left of this diagram. And thus, angle CDB is equal to angle DCA. Boop, this angle here has to be equal to this angle here, angle DCA. But what did we just show? That shows that in the original Sarcari Quadrilateral, if we remove all these diagonals and such, the summit angles at C and D have to be equal to each other. This angle CDB equals angle DCA, i.e. angle D equals angle C in the original form. This tells us then, in other words, that anytime we're looking at a Sarcari Quadrilateral, meaning if we're looking at a quadrilateral where the base angles are both right angles, and if this side has the same length as that side, then it's going to have to be the case that these angles up at the summit, angle C and angle D, are going to be equal to each other. So let's make some observations here. Go ahead and pause the video if you want the proof. I'm going to make some notes on the board and need some space to make it. So I'm going to go ahead and erase the proof. Go ahead and pause the video if you still need that. So I want to note a couple of things. We show that angle C and angle D have to be equal to each other. What did we actually use in order to get there? The only two kind of things from Euclidean geometry, tools we needed to show angle C and angle D are equal, is we needed side angle side and side side side. And that's really the only two things this proof relied on. These are kind of the only two propositions we needed before being able to prove this. Only relied on side angle side and side side side. But if you remember, we said in spherical geometry and elliptic geometry, side angle side and side 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 both still worked. There are a bunch of other things like the Pythagorean theorem, etc., that didn't work in hyperbolic or elliptic geometry. But side angle side and side side side, in fact, all the triangle congruence propositions still worked in the two models of non-Euclidean geometry we've seen in the last two standards, which both still work in spherical geometry and the Poincare disk. What does that tell us? Well, that tells us this proposition, which only relies knowing things from these two non-Euclidean models, let me start again. We know this proposition only relies on side angle side and side side side. Hello, Dr. Webster, looking at me from the doorway. And we know side angle side and side 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 still work in spherical and spherical geometry and on the Poincare disk. This then tells us this proposition is still true in these non-Euclidean models. In both models, in spherical geometry and in the Poincare disk, as well as in Euclidean geometry. Neato burrito, if you ask me. This proposition is one that works in all three, or proof works in all three models, Euclidean, spherical, Poincare disk. One other note I want to make about this proposition is that if you look at this picture, we said angle C looks like it's equal, has to be equal to angle D. It certainly looks like angle C and D also are going to be right angles. But one thing I want you to notice is we proved angle C and angle D must be equal. We did not prove angle C and angle D are both right angles. Maybe they're both 45-degree angles or 150-degree angles. All we know so far is that angle C and angle D are equal, not that they're both right angles. So we didn't show angle C and angle D are right angles. Only that they're equal. Lots of angle sizes, lots of angles that are equal out there without being right angles. And so what I'm going to do next is we know that any Sarcari quadrilateral, whether it's in Euclidean geometry, hyperbolic geometry, elliptic, or spherical geometry, and all of these three models we've seen so far, all the summit angles of any Sarcari quadrilateral have to be equal. In Euclidean geometry, they look like they're going to be right angles in this picture. And in fact, that will be true in Euclidean geometry. But now I want to take a minute and take a look at what do Sarcari quadrilaterals look like in spherical geometry and in the Poincare disk, and see how they look different than this one I drew using in the standard model of Euclidean geometry. So let's take a look. So first one I want to look at is going to be a picture in spherical geometry. So if you recall, in spherical geometry, we're looking at points and lines on the surface of a sphere, where the lines are all great circles, circles that wrap around the sphere, enclosing the maximum possible area. So let's take a look and see, what do these look like if we tried to draw a Sarcari quadrilateral on a sphere? Well, I'm going to draw the equator, and we're going to have 2 points on the equator. This will be A, that'll be our A, that'll be our B. And now, I'm going to draw lines coming from the North Pole down through A, so intersect at a right angle, and a line coming down through B, a great circle, that'll intersect B at right angles. So far, we've drawn something with 2 right angles. And now, I want to make another line. This one's going to kind of be going through and doing something like this.
and then this will be our point C, and this will be our point D. All right, purposely drew them so that these two sides, the length of the segment between A and C and the length of the segment between B and D are going to be equal to each other. So here, if we take a look at our drawing, we could say that the quadrilateral ABCD is Sarcari. It's a Sarcari quadrilateral. How do we know that? Well, that's simply because angles at A and B are both right angles, and AC is equal to BD in length. But now, I want you to notice something. We know that the angle at C has to be equal to the angle at D, because they're summit angles in a Sarcari quadrilateral, and even in spherical geometry, as we just showed, the proposition from earlier has to be true, meaning the summit angles of any Sarcari quadrilateral in spherical geometry have to be equal. But if you look at these angles here, at angle C and at angle D, do those look like right angles to you? Turns out they are not right angles. In fact, they're obtuse. Angle ACD, let's draw it a little better here. It's a little hard to see. There, that makes it a little easier to see. This angle from A to C to D is an obtuse angle. And BDC is, again, an obtuse angle, meaning they're both the same size. Well, they're two obtuse angles that happen to be the same size, but they're both greater than right angles. Gadzooks. So, and this is going to be the case anytime you look at a Sarcari quadrilateral in spherical geometry, it turns out, is that the summit angles of any Sarcari quadrilateral in elliptic geometry, in spherical geometry specifically, their summit angles are always going to be obtuse. The same size by what we proved earlier, but still obtuse. Let's see what happens if we do an example in hyperbolic geometry. So now we're going to look at a Sarcari quadrilateral over the Poincare disk. So if you remember, Poincare disk is just a two-dimensional inside of a circle. All the lines have to either be diameters, meaning straight lines cutting across from one side of the disk to the other, or they're going to be circular arcs that intersect the disk at right angles. So here, I'm going to start by drawing this line. That's a diameter of the disk, goes from one side to the other. And here, we'll pick this to be our point A, and we'll pick this to be our point B. And now, I'm going to draw some more lines passing through A and B. I'm going to draw a circular arc that does something like this. That actually intersects the original line at a right angle, and ditto with this one. So here, we just drew two lines that intersect the original diameter at two right angles. And now, we're going to draw another one that connects them. And I'm going to let this be my point C, and this, these are a bit more. There we go. And then this will be our point D. And here, I tried to draw it so that AC and BD have the same length. So if you notice, I just drew another Sarcari quadrilateral. ABCD is again Sarcari because the angles are base angles. The angles at the bottom at A and B are both right angles, and AC and BD are equal in length, the two sides. So it has everything it needs to be Cycaric. The angle at C is equal to the angle at D, which we knew would have to happen because because over the Poincare disk, our proposition from earlier still holds true, meaning the summit angles will have to be equal. But this time, do our summit angles look like right angles? Not at all. Those look very, very much less than right angles, i.e. they are acute. And just like the Sarcari Quadrilateral we drew in spherical geometry, our summit angles are still equal to each other in the Sarcari Quadrilaterals we drew. But while in spherical geometry they turned out to be obtuse, in Euclidean geometry they turned out to be right angles, and in hyperbolic geometry, or in the Poincare disk at least, they turned out to be acute angles. So if we look at this note here, we showed that the summit angles in any Sarcari quadrilateral have to be equal, but that doesn't necessarily tell us they're right angles. They will be in Euclidean geometry, but in hyperbolic or elliptic geometry, the summit angles of a Sarcari quadrilateral do not have to be right angles. They'll be equal to each other, but will be equal as obtuse or acute angles. And I think that's going to do it for this video. So in Wednesday's class, we're going to look at a different type of quadrilateral called a Lambert quadrilateral, named after a Frenchman this time. And we're going to kind of talk about how a Lambert quadrilateral is different in Euclidean versus spherical versus Poincare disk geometry, and kind of tie that back together to how do properties of lines and such differ in the three different models of geometry. Hope you're all doing okay. Hope you all had a good Thanksgiving, by the way. Even if you maybe didn't get to see as much family as you wanted, or food wasn't as good, I hope you still had fun and you're still healthy and safe. And I'll see you again in Wednesday's class. Take it easy and remember, you got this.